Hello everybody. In this video, I'm going to show you how to find out the internal loading because of the external force on any structural member. Okay? So internal force, that's what we are gonna learn in this video. If you see here, I'm showing you a cantilever beam and there is no external load on that. Just assume that the beam itself is weightless, then basically there is no internal force working down there. Similarly, there is let's say a chain here hanging from the wall, and if you don't have any load here, then basically you don't see any internal reaction. What is that internal reaction actually? Means like when the material, let's say for steel, like there is no load there, then all the particles are like the molecules are in their own position, right? So when you apply external load, that will cause either like compression or tension of the molecules, and they will try to hold that one together. Okay, so if you apply too much load there, what will happen? The molecular force balance will be lost, and then you will see that the material is gonna fail. Okay, for engineers, it's our duty to design the material based on like different thickness and size so that it can take the required force for that particular member, right? Let's say here, like for a beam, if I apply load here, then you see this beam will try to rotate like this one. There will be a compression force in that direction and a shear force in that direction. Usually when we make a cut of a rigid body, there will be three component of reaction. Okay, you cannot see that one in the material from outside, but you have to make a imaginary cut there to see that, hey, what are the forces working down there. Similarly for cable, if I add a load here, let's say this is 100 pounds, then basically you will see that the cable or the chain is kind of stressed inside. Okay, if you increase that load from 100 to 1000, then the stress will increase, and if you increase more and more, you will see at a certain point this cable can fail, right? So what we do, if we need like to hold too much external load, then basically we have to get a thicker or bigger size, like cable down there, right? That's the way we design. We are not gonna design anything in this course, but if you have that idea of internal loading, then basically you will be able to solve some of the problem in your future course, which is called the strength of material or mechanics of solids. Okay, but here we are just going to give you some introduction that how you can find out the internal loading here. Okay, so to find out the internal loading, as I said earlier, that you have to make a imaginary cut. Okay, where you have to cut? You have to cut at that location at which you are trying to find out your internal loading. Okay, for example, if I want to see that how many bones is there from outside, I don't see that one. Okay, so if I make a cut and take that one, that how many bones I have here, then I'll see that there is 2 bones here, right? But if I need to see that, hey, how many bones are there, then actually you have to make a cut here. Okay, and if you cut it and then see that one, you will see there is just 1 bone there, right? So what you have to do, that you have to make a imaginary cut at the location at which you are trying to find out the internal loading. The other thing you can see, as soon as you cut it here, you will see 1 bone coming this side and 1 bone is coming from this side, and actually when you put them together, you don't see that bone anymore, right? The same analogy you can use here, that when you make an imaginary cut, you will see like three component of reaction for a rigid body, and they are equal and opposite. When you put them together, actually from outside you don't see anything there, right? So here, let's say for here, this is a cable. If you cut a cable, then basically you will see one component, and that component is always tension. You already know that one, because this one will not take any bending moment or shear force, because they can't, okay? They will just bend. They don't show any resistance for bending. Now if I make a cut here and see that how much load is coming here, then basically if I cut that one here, I can just show that one here, and if I see that if the whole thing is in equilibrium, then a part of that thing is also in equilibrium. If I take the summation of forces in y direction, then I see this one is 100 pounds. So this one has to be also 100 pounds. So I can see the tension inside that cable is also 100 pounds, right? Similarly, if I take a load, let's say this is 100 pounds, and this one is, let's say, 3, 4, 5. Okay, and if I make a cut here, since this is a rigid body, so this one will show three component of reaction. This one we call that one normal force, which is basically perpendicular to the cut surface. Okay, perpendicular to the cut surface or along the longitudinal axis of that member. Okay, and shear force is perpendicular to the longitudinal axis of the structural member. And similarly, you can see this one is your bending moment. Okay, now if you think like, hey, this one is in equilibrium, then basically you can find out this one, and this one quite easily. Okay, now the question comes like here, that whether this one is compression or tension, or this one is downward or upward, or this one is counterclockwise or clockwise, right? So we don't know. We can assume at the beginning anything and try to solve the equation of equilibrium, and if you see that I'm getting a positive number, then basically your assumption is valid, or if you get a negative number, this means like your direction would be other way around. Okay, but for this particular case, for internal loading, actually there is a sign convention. Okay, so the sign convention looks like this. Like if you, let's say here, I'm just trying to show that one. If this one is in tension, then we call that one positive. Okay, so tension positive, and compression is negative. So compression is this way, right? Trying to push that one here. Similarly, if I show, let's say here, if I show that one here, okay, we usually denote that one as V, V like Victor, and if it tries to rotate that one counterclockwise, then basically this is negative. If it try to rotate that one clockwise, then it would be positive. Okay, so we can write clockwise rotation. It will not rotate. It will try to tend to rotate that one clockwise, then it's positive. And counterclockwise rotation, that's actually negative. Now you can see if I have something like this, and I got that one here, let's say, cut that one here. So if this is downward, this one has to be opposite, so this one is upward, right? If you think this one is trying to rotate that one clockwise, you can see this one is also trying to rotate that one clockwise, so this one is your positive shear, okay? If this one is other way around, now you can see this one is trying to rotate that one counterclockwise. This one is also trying to rotate counterclockwise around that cut member. Means like this one is negative. Okay? Now let's talk about the bending moment. Let's say I have my moment here. Okay? So to see that one little bit, better, actually, sometimes let me take that one here, like for this one here. You can see this one is trying to go like this. I'm just extending and putting that head at the top or bottom of the member. If it is this way, then I'll just took it here. Now I'll try to see that this one is actually trying to make that one like this, right? If it push that one, then this one will go like this. Okay? So try to remember that one. When this one is like this, and when this one is like this, then this is positive. Okay? This is negative. Sad face is negative. Smiley face is positive. If like this one here is trying to make that one sad face, so this is negative. If I have a moment like this, which is actually trying to make that one like this, then basically this one will be positive. You can see that one a little bit different way though. Let's say any rigid member here, okay, and I am trying to show that one like a rotation like this, a bending moment like this, okay? So what will happen, like if this one has changed? You can see this one will try to go like this. This is the neutral axis of that beam. You can see because this one is trying to push that one down, so this one, the size of this one is a little bit smaller than this one, and definitely this is the longest distance. So this one is under tension and this one is under compression. Same member, but the top fiber is under compression and the bottom fiber is under tension. Okay? This one is positive. You can also see this is your smiley face. So this is positive. Okay? So we can also say upper chord under compression is positive. Okay? Similarly, you can see when you are trying to do that one, let's say pushing that one here, this one is gonna go like this, and you can see the bottom chord is under compression. and that's negative. Okay, so bottom part under compression is negative. So what we will do, like at the beginning, we'll assume that the normal force, shear force, and the moment is positive. Okay, if I get positive number, then my assumption is okay. If I don't get positive number, then basically I have to reverse the sign. Okay, so what is positive? Let's say when I cut a member 3D, when I cut a rigid member, then basically I'll show that one in such a way that this one tension is happening there. Okay, at the beginning, that's my assumption. Okay, I'm assuming that my shear is positive, means like trying to rotate that section the counterclockwise way, and I'll try to put that like bending moment in such a way that this one is creating a smiley face or positive moment. Okay, if I get positive number, then I'm fine. If I don't get a positive number, then basically I have to change that one. Okay, now let's try to see some of the problems here, that how we can find out the internal reaction. Okay, so here first we'll try to solve problem number 7-4, which is saying this is your a beam which is 280 pounds per feet here. Okay, and this one you can see this is 6 and this is 8, so the total distance is 10 from here. They are asking find out the shear force, bending moment, and normal force at point C here. Okay, at point C. So I can, to find out that internal reactions, I can just cut a section here. As soon as you cut there, you have to show that one with 3 unknowns: normal force, shear force, and bending moment, right? So if there is another unknown there, then basically we will have more than 3 unknowns. And we have only 3 equations of equilibrium: summation of Fx, summation of Fy, and summation of moment equal to 0, right? All the three summation of forces and summation of moments are 0, right? So we have 3 equations, we can solve only 3 unknowns from there. So if I have more than 3 unknowns, then basically that won't be difficult. That would be difficult for me to find that out. Okay, eventually that would be actually impossible. So what we usually do before we make an imaginary cut, we try to find out the other unknowns here. Okay, let's say here what we can do, I can find out the reaction here and then make a cut. So if I consider the bottom part or upper part, then basically bottom part I have 3 unknowns here. Similarly, if I find out this one here and then cut it here, then basically I have to have I'll have 3 unknowns here, and that would be easy to solve, right? So now let's try to solve this one here. So I'll take this reaction off and show that one. Let's say this is AY, this is AX, and this is perpendicular here. Let's say that's BX here. Okay, and the total load you can see, since this is 280 pounds per feet and I have 10 feet, so this one has to be 2800 pounds. Okay, now I can find out this reaction and this reaction from A. So you can see if I take a moment here, then B is counterclockwise. So Bx multiplied by the distance. So this is the line of action of that force Bx, and from here to here is 8 feet. Okay, then I can take this one minus 2800 multiplied by the distance of the from here to here, line of action of this one, right, from here to here. So this one is at the middle. The centroid for a rod is just at the middle point here. So from here to here is 6. So from here to here that would be 3 feet. So if I solve for Bx, so once we get that one, then basically I'll just make a cut at this point here. Okay, I can see if I make a cut, I'll have three, like forces here, but I will also have like this force and this force. So if you want to find out like AX and AY and cut that one at C and consider the bottom part, that's also a good idea. Okay, so let's try to do that one. Okay, so if I know this one, then I can find out from summation of Fx you see Ax minus Bx equal to 0, so Ax is also 105. Similarly, if you take the summation of Fy equal to 0, then basically Ay minus 2,800 pound equal to 0, so Ay is also, Ay is 2,800 pounds. Okay, now you can make a cut here. You can either consider this side or consider that side, that's up to you. Okay, for here I'm just gonna do that one only like here. I'll request you though to find that out using the other side by yourself and see whether you get the same answer or not. Okay, so this is the drawing of the, after cutting that section at point C. You can see I'm assuming that the normal force working along the longitudinal direction of the member, this is at the beginning, I'm assuming this one is positive, means like this is tension. Similarly, I'm taking the shear force BC, which is downward, so means this one is trying to rotate that one clockwise direction, so it's positive. And then I'm trying to take the moment in such a way that this one is gonna drop that one, this one is make that one a smiley face here, so this one is positive, right? And at the same time you can see now the weight of this part, which is actually 3 feet here, so the total weight would be 280 pounds per feet into 3 feet, that's actually 840 pounds, which is actually 0.84 kg, right? Similarly, I have my 2.8, AY, and this is my AX here, which we got from the previous thing, and here is your theta, and your theta is basically tan inverse 8 by 6, that's actually 53.13 degree here. Okay, so now you can see I have three unknowns here, NC, VC, and MC, and I have three equations, so it's easy for me to find out that three unknowns here, right? So let's try to do that. So summation of fx equal to 0. Actually, I'll just take this one is my x direction and this one is my y direction. Okay, that would be easier. So let's say this is positive here. So NC, now if you come here, then basically you see this one would be plus 1.05 cosine plus 2.80 sine 53.13 minus, I'm just taking this one, and the component of this one, which is 0.84 sine 53. That's equal to 0. So from there, I can find out my NC, which is basically 2.2 keep. I got a positive number, which means like actually my assumption is fine, right? So this is actually tension. Okay. Now take the summation of forces in the y direction. Let's say this is positive here. So you can see minus VC minus 0.84 cosine 53.14 plus 2.8 cosine 53.14 minus 1.05 sine 53 point, actually 13. That's equal to 0. So I get my VC is equal to 0.336 key. Again, I got a positive number. This means like my assumption is fine, right? Now take the summation of moment at point C here. Okay, so summation of moment at C equal to 0. Let's say counterclockwise is positive. So you can see MC plus 1.05 cosine sine 53.13 multiplied by 3, then minus 2.8 cosine 53.13 multiplied by 3, and then plus 0.84 cosine 53.13 multiplied by 1.5 because this one is working, the distance from here to here is 1.5. So that's equal to 0. So I get my MC is equal to 1.76 cube feet. And once again I see that this one is positive, so means like my assumption for moment is also correct. Okay? So let's move forward and see some more examples. Problem number 7-13. Okay? Here is the figure. This one is saying determine the internal force, internal normal force, shear force, and moment in the beam in section passing through point D and E. Point D and E. Okay? The point D is located just to the left of the 5 kip load. Okay? So point D is just left. So if I cut at the point, like D, then basically this load would be at the right side. Okay? Because this point is just left of that point. Very small amount. Okay? Now you can see here that actually there is a fixed support here. So there is 3 unknowns here, and I have like a roller here, so 1 unknown. So total number of unknown is 4. Now it's kind of difficult to find out like if you have 4 unknown reaction, right? Because I have 3 equations. Summation of fx equal to 0, summation of fy equal to 0, and summation of moment equal to 0. But one of the good thing here that they showed you that actually the beam is not constantly like going from A to C. This one is showing that at point B there is a hinge, okay, there. So what you can do, you can just open that hinge and show that one with 2 force reaction, right? That's what I did here, okay? So you can see this is your, actually, that's your point A, this is B, this is C, and this is actually point B here. So you can see, I just assume this one is my Bx, this is By. Since I opened that one, then this one is in the opposite direction, is downward and this way. So that when you mix them together, actually you don't see any force like here. You don't see any force here, right? Now if you see that one, and if I consider the left side here, you can see I have only 3 unknowns here, A, Y, B, Y, and Bx. So I can find out the 3 unknown By and Bx. Once I know By and Bx, then I can consider the right side, and then I have 3 unknowns here. If I want to, then basically I can find out all the unknowns here. Okay? Now what happens like if I try to see my reaction here? So what we'll do like take a moment at point B. Summation of moment at point B equal to 0. Let's say this is positive. Okay, so that's 6 plus 5 multiplied by 6. So this one is 6 is already a moment. So you don't have to multiply with the distance. Here is your force 5 into the distance 6, and then minus AY multiplied by 12, that's equal to 0. So your AY is basically 3 kip. Okay? If you take the summation of fx, since there is no external load in the horizontal direction, so basically you see Bx equal to 0. Okay, no Bx there. And if you take the summation of forces in y direction, that's equal to 0. So you can see AY plus BY minus 5 equal to 0. So BY equal to 5 minus AY, 5 minus 3, that's actually 2 cube. Okay? So once we get that information, I'll not go there because I'll make a cut here. That's actually a point E. And I'll consider this side here. Okay? So let's try to find out the internal reaction for C. So what we have to do, that's actually my C here is 3 kip. This is 6 kip feet. And I make a cut at C. So if the point C is left to that force here, so when I cut at C, actually the force was a little bit right side, so it didn't come here. Okay? So if it doesn't show here, so I'll just say this is my CX. Not CX, sorry, I'll just put that one. NC, normal force at C, shear force at C, and bending moment at C. Okay? So here you can see I have 3 unknowns here because I already know this one, right? So I can find that out easily. First of all, there is no summation of external force here for x direction. So summation of Fx equal to 0. So actually NC equal to 0, right? Take the summation of Fy equal to 0. So you can see 3 minus Vc equal to 0. Actually, this is point D here. I made a little mistake here, D, so that would be ND, MD, and VD. So first of all, we got ND equal to 0, and then you can see your VD, that's actually 3. I got a positive number, so this one is positive shear. Okay, and then summation of moment at D equal to 0. Clockwise is counterclockwise is positive, so MD, this one is also counterclockwise, so this is plus 6, and this is clockwise, that's actually 3 into 6. 3 into 6, that's equal to 0. So MD is equal to 12 kip feet. Again, I got a positive number, so my moment is also okay. Okay? Now let's try to move here and try to see, hey, what is the internal forces at point E. Okay, you can remember that, like when I tried to show that one here, if I want to find out the reaction here, then basically I have to simplify that one. Okay, but when you are going to find out the internal reaction, then basically you have to make a cut through the distributed load too. So for example here, I know my Bx equal to 0, so I can just show this part here. Okay, this is my point E, and this is my force here is B, which is 2 kip. I already find that out, right? So I know this is 2. I'm just cutting a section here and considering this part, left part here. If you want to consider the whole left part from here to here, you can do that one too. But since I know already like what is the reaction at B, so I'm taking the smaller part. Okay, if you take the whole left side, you can do that. If you want to do the whole right side, you can do that too. Okay, so here, and then you can see the distance from here to here is actually 4 feet. So here is your, when you cut that one, actually you have to cut the distributed load too. So you made a cut here, so you have that distributed load too. Okay, so this one is 4 into 1.5, that's actually 6 now. So once I cut that one here, then basically I have to show that one a simplified form. So this one is working at the middle and this one is 6 kip. Okay, since I made a cut here, so this is NE, this is VE, let's say this is my ME. Okay, so I have 3 unknowns here, I have 3 equations, so it's easy to find out the forces here, right? So first of all, you can see summation of Fx equal to 0. So Ne is equal to 0. Then summation of Fy equal to 0. So you can see minus 2 minus 6 minus VE, that's equal to 0, right? So VE is equal to minus 8 kip. So actually I assumed that this one is positive, my shear is positive, but actually it's not. So this is negative shear. So you have to, since I got a negative number, so this is negative shear. Okay? Similarly, I assume this one is positive. If I get a negative number, then I have to say, hey, this is a negative moment. Okay? So let's say summation of moment at E equal to 0, let's say counterclockwise is positive. So ME, that this one 6 into 2, that's also positive. And then this one is 2 into 4. That's equal to 0. So your ME is equal to 20 kip feet. Since I got a negative number, so my moment is not positive. Okay? So this is negative moment. Okay? Let's move forward. Problem number 7-20. Okay, so you can see the figure here. This one is showing that there is a triangular load here, a concentrated load, which is 60 pounds that's working at this point, and then you have a triangular load here. There is a roller here, and which is on a plane which is 30 degrees with the horizontal, and there is a collar here. Okay, collar. The collar can go up and down, so this one doesn't have any resistance towards the vertical direction, so no component of reaction in the vertical direction. But if you want to move that one horizontally, it will not allow you to do that one. It offers resistance against the horizontal movement, so I have horizontal force there. At the same time, if you try to bend that one, since this collar doesn't have any pin here, so basically this one would offer resistance for bending too. Okay, so now first let's try to find out the reaction. Maybe we can just try to find out the reaction here first and make a cut at C and consider the right side. Okay, now this one is saying that determine the internal normal for shear force and moment at point C, which is located just to the left of the 60-pound concentrated load. So just to the left, this point is just to the left of this 60 pounds load. So if I cut at C, actually 60 would be there. Okay, now let's try to find out the reaction at point B, A and B. Okay, so let's say here, if I take that one here and show that one a normal force in this plane, which is actually, let's say, R at B, and you can see from here that this is 30 degree here and this is 90 degree here, so this one is making 60 degree with the horizontal, right, or 30 degree with the vertical. So, and then I can just show that one here at point A. I don't have any vertical force here, so I have, let's say, this one, and this is AX, and this is moment at A. Okay? Now what we can do to avoid that moment, I can just take the summation of forces in Y direction. So if I take the summation of, not moment, summation of forces in Y direction, so I have to simplify that one first, right? Hey, I have some force here, which is basically this triangle. That would be half into this distance into 15, so 3 into 50. Okay, similarly I have one force here, which is half into 1.5 into 50. Okay, now you can see the summation of Fy equal to 0. So you can see RB is making 60 degree with the horizontal. So if I take the vertical component, that would be sine 60 minus that's 22.5 minus 60 minus 11.25, that's equal to 0. So your RB, that's actually 105, 108.25. 108.25. okay, 108.05. So what we can do, since I already know that one, I can make a cut here. And since this load is just to the right of this point C, so I can see this concentrated load there, okay? I can see this concentrated load just right to that point C. Okay, and this one is actually 108.25 pounds. So as soon as I cut that one here, I have to show that one my NC. I'll show that one like this way, trying to rotate that one clockwise. That's my VC, and a moment here which is MC here. Okay, so once I get that one, then basically I have three unknowns here and I have three equations, so I can find them out easily, right? So let's say summation of fx equal to 0. Let's say this is positive, so you can see minus NC minus 108.25 this way is cosine 60 that's equal to 0. So you can see your NC is equal to cosine 60 is half, so this one is 108.25 multiplied by half. That's actually 54.1. Okay, that negative sign means like that this one is actually not tension in tension, it's in compression. Okay, now let's try to find out the VC. So I can take the summation of forces in y direction. Okay, so you can see your VC, then minus 60 minus 11.25, that's actually plus 108.25 sine 60. That's equal to 0. So your VC equal to minus 22.5 pounds. Okay, so that's a negative shear. Now I can also take the moment at C. So summation of moment at C equal to 0. Let's say counterclockwise is positive. So you can see this one is the negative minus MC plus 108.25 cosine, sine 60 So this one is sine 60, the vertical one, multiplied by 1.5. And then minus this one, multiplied by the distance, which is 2/3 from here, so that's actually 1, that's equal to 0. So your MC is equal to 135 pound-feet. So basically I got a positive number for the moment, so the bending moment is positive, whereas this shear force and normal force is negative. Okay? Thank you for watching.